This video shows how to use a Keyestudio Relay Shield with a Raspberry Pi and Node-RED software. You may also be interested in our two companion videos, how to set up Relay Shield and Relay Shield electronic workbench testing results. Here's an outline of the rest of the video. We're going to examine the hardware, then examine several example Node-RED flows, and finally I'll provide some free project design advice that's worth every penny you paid. First, we take a look at the hardware. You could lay everything out on a table or in a shoebox. I made a little wooden half box to organize the parts. This case is three pieces of scrap exotic hardwood in an H shape with rubber feet on the top and bottom. The Pi and other equipment hang underneath the top, so it can sit on my shelf and look nice and be protected from dust when it's right side up. Yet when I flip it over, there's easy access to the Pi and the wiring. It's hardwood, so I can drill and tap 440 size machine screws for mounting. Underneath the Keyestudio Relay board, I have a PiJuice battery power system installed, so I have a completely wireless floating ground relay switching system. The power supply is from Amazon. It's a 12 volt to 3 amp USB microconverter with a standard amateur radio Anderson power pole DC input plug. You can buy very small diameter machine screws that easily fit through the Anderson power pole roll pin hole, like an Imperial thread number 2 by 56 screw will work. And then you can add some nylon washers to space it off of the board. It's important to note the layout of the relays, held such that the Pi USB ports are to the left and the relay screw terminals are to the top. The leftmost relay would be relay J5, and the rightmost relay would be relay J2. In other words, the relays are in descending order, and there is no J2 or J0 relay. Of the three screw terminals for each relay, the normally closed contact is to the left, the common is in the center, and normally open is to the right. So when the relay is off, the two terminals to the left are shorted. When the relay is on, the two terminals to the right are shorted. If you hold the Pi with the Ethernet and USB cables hanging downward, the J2 relay would be at the top and the J5 relay would be at the bottom. The simple relay demo has three main points. The first is that nodes take a message.payload, and the result is that they turn the relay on or off. The second point is nodes accept a wide variety of messages. And the third point is that nodes have help files. Let's load the relay demo. First, we'll go to the hamburger menu, import, examples, the relay shield, the demo, import, select the tab, click on the red deploy button, and it works. What's going on with these injectors is they send a message.payload of on, or in this case off, or numerics like 1 and 0, or strings like true and false. And those go to the nodes that control the relays. You can see those in the node palette along the left side of your screen. If you scroll down, there they are. You can just click and drag onto the screen or delete. If you select one of the relays and select the little book icon, you can see the help file. And it goes into great detail. There's 4 ways to turn a relay on. You can send a message.payload of on, 1, set, or true. And there's 4 ways to shut off a relay. You can send a message.payload of off, 0, reset, or false. You can also delete the flow when you're done. You go to the hamburger menu, flows, delete, and click deploy. And that was a simple relay demo. The next demo is the microwave sequencer. That demo has three main points. The first point is messages can cascade through multiple built-in nodes. Also, you can have multiple output and multiple input connections. All node red connections look like wires on the screen, but they're really diodes. Outputs always go to inputs. Two connections to the same input are not connected in the sense of a wire like would be physically. The final point is the demo also shows how trigger nodes can clean up incoming messages while also doing some time delays and other features. Okay, let's try the microwave sequencer demo. Hamburger menu in the upper right corner. Select import. Select the tab for examples. Go through examples, flows, relay shield, microwave sequencer demo. Click the big red import. Select the new flow. Click deploy. Give it a try. If you click on the transmit, it sequentially turns things on. If you click on receive, sequentially turns them off. First of all, note you can have multiple input and output connections. The trigger here, this trigger node that I'm highlighting here, has two outputs. It goes to the next trigger node, which goes to the next, which goes to the next. The other output is it goes to the input of the relay. Now, the relay also has two inputs, and in Node Red, wires are basically diodes. So the output of this trigger is not in any way connected to the output of that trigger, even though they both connect to the same input. So this is not like a schematic diagram where power comes through here. Say power comes through here, then it flows through here, then it flows through here. So turning this on would make you think it would trigger this node, but wires are diodes in Node Red. Doesn't work that way. The next point is messages cascade through these nodes. So when you send a transmit message to this trigger, it sends an on, and then it waits and it does nothing. But that goes to the next trigger, which does nothing. It waits, and then it turns on, which goes to the next trigger that does nothing. Then it waits, then it sends an on, and so on until all four have been triggered. Then, in the opposite direction, it works exactly the same way. If you go in receive mode, it turns this one on, then it feeds into this, and it turns that one on, then it waits a tenth of a second, turns the next one on, and so forth. So when you turn it on, they go in order. When you turn it off, they go in backwards order. This is pretty basic microwave sequencer. It just has a LNA that would turn on when the relay's off, a transmit receive relay that goes into transmit mode when the relay turns on, a power amplifier that would turn on after the transmit relay is turned to transmit, and a transmit inhibit disable, which is a double negative, but basically it makes it okay to transmit. That would be your microphone pin, or if you have a radio that actually has a transmit inhibit pin, that would disable it when J2 turns on. It's kind of basic. It looks like it would actually work. You would be using GPIO pins instead of clicking buttons in your Node Red. and then you would hook up your push to talk switch to a GPIO, and you would probably just make the receive the opposite of transmit. You have to add a little bit more to this, because if you were to transmit and receive in less than 400 milliseconds, the transmit cycle would not complete before the receive cycle initiated. But I mean, this is just a basic demo. Um, I haven't put it on a scope. As far as I know, the delays are 100 milliseconds. Um, Professionals would want to detect that the relay is the transmit receive relay is actually switched before enabling the power amp. Some relays have an auxiliary contacts for that. Um, Another thing that this does demonstrate, which is interesting, is the transmit payload could really be anything. I'm sending an on. It could be, just whatever. It doesn't matter, because the trigger will trigger on any input. And in this case, it sends an on, which cleans it up. So the on will turn on relay J5. It'll also set off the next trigger, regardless of what the content of the payload is. You could send it anything, really. So it's a pretty good demo of what you could do with microwave sequencing. It's not a perfect sequencer, but it's a start. And then when you're done, you just delete the flow and redeploy to erase it. So hamburger menu, flows, scroll down to delete, click deploy, and it's done. Good news for fans of quality 1970s music. Disco is not dead, and I have a example disco light sequencer in nodered to prove it. It also demonstrates that nodered has state variables that belong to a flow, and you can write to them or read from them to control the behavior of your overall flow. And another common design pattern is demonstrated, where you have an endless loop, and you can modify what it does in the process of the loop based on the state variables. And finally, it'll demonstrate that delay nodes have a optional random function, which might be useful for other purposes. Okay, let's hit the dance floor. Demonstrate the disco light sequencer. Upper right hamburger menu, scroll down to import, select the examples tab, scroll down to the relay shield, select the disco light sequencer demo, import, goes into a new tab, select the tab, click the big red deploy button, and there you go. It should automatically start upon load. For copyright reasons, you'll just have to imagine this is connected to a Y, relay J4 is connected to a C, relay J3 is connected to a M, and relay J2 is connected to an A. So you have Y, M, C, and A, as per the song that I can't include for copyright reasons. What you're looking at in the upper left corner is a mode select, where you can stop this thing, and then once it gets to the bottom, it will simply stop. Or you can select start mode, and it'll start it back up. So the start injector just injects an off, which is a long story why. It'll make sense a little later. The stop mode injects an on. Those go up to set flow state. Now what that is a node built into nodered that lets you customize it. So it's a change node. So you're setting flow.state in this dropdown to the value of message.payload. And that's how you set a flow wide state. Endless loops are a pretty common design pattern in Node-RED. So this trigger feeds into a random delay, which feeds into a trigger, into a random delay, and so on and so forth repeatedly. Eventually it reaches the bottom, comes right back up and starts again. In this trigger, see, it sends an on that turns on relay J5, and then it waits a little while. Then this random, it delays for a random amount of time between 100 and 2500 milliseconds, at which point this trigger sends a off, and that pretty much just repeats. The way you control it and turn it on and off using those variables is at the bottom. This trigger doesn't just go back to the first trigger to make a loop. It hits a switch, and the switch, depending on message payload, if it equals flow.state variable, it goes out the first port. If it does not equal the flow.state variable, it goes out the second port. So in the first scenario, it goes up here. So there should be a off sent by the last trigger, because the off shuts off the last relay. So that's why the logic seems kind of backwards. I did that on purpose. It's a little obfuscated. You wouldn't really do that in practice. You would probably make the start mode be on and the stop mode be off, and then you would just hook it up to the opposite output of the switch. But this kind of forces you to think about it. So a off comes from the last trigger. If that equals flow.state, which is off, then it continues to run. It comes back up to the start. And if it does not equal the flow.state, because it's something like on, if flow.state is on and it just received an off message payload, it would go out the second port and go absolutely nowhere and just stop. And so that's how stop mode is engaged. And it automatically starts down here, inject once after a tenth of a second, and then never repeat. So that's how you turn it on, and it goes Y, M, C, A randomly, with random duration between the lights turning on and off. Click stop, it'll just stop at the bottom once it reaches the switch. And there you go, they're all off. Anyway, once you're done with the disco, you go to the hamburger menu, scroll down to flows, select delete, select deploy, and it's erased. One more visit to the disco. This time we're going to look at a light blinker demo. The purpose of this is to show how debug nodes can be used as a general purpose display. They're not just for debugging. You can uh, look at your flow and see what the current state is. Time for our last trip to the disco. We're going to load up the disco light blinker demo. Go into the hamburger menu, go down to import, select the examples tab, select the relay shield, the blinker demo, click the big red import button, click the big red deploy button, take a look at the tab. Here it is. You can turn all your relays off by selecting 0% on time. You can turn all your relays on by selecting 100%. Half of them on and half of them off by 50. You can hear it clicking in the background. You'll note over here, this percent time on debug node lists the percentage underneath it. The way that works, these injectors just feed in a numeric percentage. Message payload is a type number. giving it 50%. Comes into a change node where you set the flow.onPercentage state variable to the value of message.payload. And it just passes through whatever message payload is to a debug node, which outputs message.payload in the node status. Now, by default, when you set this up, it's probably just going to have debug window enabled. So you have to uncheck that and check node status. And then you can change the name to %time on. So then when I change the %, it changes down here. I'll set it to 50%. Instead of having a loop like some previous examples, this just has a tick. The tick is an injector. It injects a message payload of on every second down here. So inject once after 1 second, then every 1 second, it injects another message payload of on. Then that hits random. The payload doesn't actually matter. When random gets hit by any payload, it'll output a new message payload that's a whole number integer from 1 to 99, not 0 to 100. I want to be able to shut it completely off or turn it completely on. It'll make sense in a second. Then there's a switch where, based on message.payload, if message.payload is less than or equal to flow.onPercentage, comes out the top. If it's greater than flow.onPercentage, it goes out the bottom. So let's say flow.onPercentage was 80 and the random number was 90. That would be the random number being greater than 90 is greater than flow.onPercentage. So it would, in that case, shut off. Most of the random numbers that would come in would be greater than flow.onPercentage if you selected 0%. Whereas if you select 100 for flow.onPercentage, basically all of the numbers have to be less than or equal to 100 because the random number generator only runs from 1 to 99. So the end result is the top output will get a message the same percentage of the time as flow.onPercentage, and the bottom, which is the direction that shuts it off, will get the remainder. And then that just hits a trigger that cleans it up. Anything that comes in, just send it on and then do nothing. And the bottom output is connected to a trigger that, unsurprisingly, anything that comes in, change it to send an off. And then those feed into the relay. On average, it seems to work pretty reliably. Anyway, I'll shut it off. Done with the disco. Select the hamburger menu, flows. Hamburger menu flows, delete. Click deploy, and it's done. The last demo is a traffic light demo. Its main purpose is to show that you can do a mode type operation in nodered, but it can be tricky to manage safely. All right, let's try a traffic light blinker demo. That's the hamburger menu in the upper right corner of nodered. Select import. Select the example tab. Select the relay shield. Select the traffic light demo. Big red import button. Select the tab. Click deploy. Here's some traffic lights. J5 is connected to a imaginary red. J4 is connected to an imaginary yellow. J3 is connected to an imaginary green. In the upper left corner, we have some operation modes. there's an auto start button, which should auto start it in normal mode. So it displays red for about 3 seconds, then it displays yellow then it displays green for 2 seconds, then it displays yellow for 1 second, goes back to red, based on flow.state and a very large switch. What we have here is a typical endless loop design. So red feeds into green, feeds into yellow, eventually feeds back into red. You can select your state by just injecting what it is. You can inject a normal mode, and then it goes into a set flow state change node. You can inject flash in red, flash in yellow. You can shut it all off. What's interesting to see is if it's currently displaying green, you don't want it to instantly display red. You want to wait for the cycle to complete until it's safe. So if you were to wait for it to display green and then click on flash in red, it'll go to yellow and then flash red. And that mode operates the same way as an endless loop. It goes and turns it on, then it turns it off, then it goes back to the switch. The switch has 4 different outputs, so it can decide what mode to re-enter based on the state, whether flow.state is normal, flash red, flash yellow, or off. Flash yellow does about what you would think. Again, with this, when you switch modes, you have to wait until the red light shuts off before you turn on the yellow light. Otherwise, you'd be displaying a red and a yellow, which is unsafe. So if I can try to click yellow while it's on, it waits to shut off and then turns on the yellow. Somewhat safer. And then you can shut it all off. Probably like 30 years ago, I had a microcontrolling professor who enjoyed assigning a traffic light controller to kids who were learning how to program microprocessors because it's so easy to mess up. It's easy to switch from displaying green to instantly displaying red, or to allow it to go from a green state to a red state without passing through a yellow. It's more complicated than you would think. It's an even bigger mess if you had full 2 directions, but that would require 6 relays, and we only have 4. But at any rate, when you're done playing with the traffic light controller, you can go to the hamburger menu, select flows, and delete, click the big red deploy button, and it's erased. You probably could use that flow on like a model railroad. Might be interesting. Anyway, that's the last demo. I have some free design advice for you. It's worth every penny you paid for it. When you design your application, you should plan on the relays all being off when the Pi first boots up. If I reboot the Pi at the command line, the Pi BIOS or some software component of the Pi shuts off all the relays. However, Murphy's Law implies there is almost certainly some way to crash or lock up the Pi such that a relay will be stuck on, uncontrollable. You want to design your application to tolerate it. Put in emergency off switch, put in limit switches, hook up things like heaters and stuff to timers, high temperature cutouts, things like that. Each relay that you turn on will increase your 5-volt power drawn by about 70 milliamps, at least per the data sheet. So turning on all 4 relays will cost about a quarter of an amp of 5-volt power. So that's about 1.5 watts. It's a pretty substantial fraction of the total power consumed by a Pi. Historically, there were problems like with the Pi version 4 in the old days, drawing so much power from the 5-volt supply all by itself that it could cause shutdowns. So adding another quarter amp or so might push a borderline power supply over the edge into shutting down. So if you're having strange spontaneous reboot problems, or if the thing shuts off every time you turn on all four relays, it's a power supply problem. You just need more current. As mentioned in the testing video, which is a pretty good video, the relays are specified to 10,000 electrical operations versus 10 million mechanical operations on the datasheet. That doesn't mean the relay will fail totally at 10,001 operations. It probably just gets slightly higher contact resistance. Maybe you can't run the full current through it. I would advise not pushing the limits of the technology too much beyond 10,000 ops. So now the datasheet does imply that the relay will mechanically fail after 10 million switching operations, so you can hear it click 10 million times. I would interpret that as meaning the contact resistance for more than 100,000 or so ops would be higher than the specified maximum contact resistance of 1/10 of an ohm. I'd be nervous about pushing full current through it that many times. As a thought experiment, let's say you switch a small LED lamp that just draws 1/10 of an amp at 12 volts, and the contact resistance soars to 1 entire ohm at 100,000 ops, and the relay contacts would drop about 1 milliwatt of heat, and your 12-volt LED would get only 11.99 something volts. It'll work fine. It's fine. On the other hand, let's say you tried to run a 115-volt wall outlet powered air compressor that draws 15 amps through those worn out contacts. That 1 ohm would drop 15 watts of heat. I'm well aware that 15 watts of heat over a couple of minutes would eventually melt the solder on the circuit boards. You could have a fire or something, I don't know. So 1 ohm is a way of saying it'll drop 1 volt per amp. So if you tried to draw 15 amps on an air compressor, that would drop 15 volts. So suddenly your 115 volt air compressor is only getting 100 volts. Maybe it'll stall out. Maybe it won't even start. It could be bad. So I wouldn't push the limits. It's also worth thinking about what 10,000 means versus 10 million. 10,000 operations in a hobbyist application could be 100 switching operations each and every weekend for about 2 years, which is, a long time. If you're just doing something with a amateur radio station or a model railroad or something. On the other hand, if you made a hobbyist project that made a ticking sound, like an analog clock pendulum or some sort of clock type thing, the relay could tick every second for 115 days, which is very short if you think of it like a third of a year, or if you think of it as something you only show at a convention or to show off to your friends occasionally. That 115 days might last like 10 years of wall time. Consider a hobbyist application like turning the low voltage LED lights on in the morning and off at night on something like a tropical fish tank. It's not really a sensitive application. Maybe 100,000 operations might survive. And at that lifetime, one operation per day would last for 274 years, which is a long time to turn the lights on and off on an aquarium. Consider using this relay as an amateur radio transmit versus receive relay. If you used it once per week for one contact per week, which would be like maybe 10 operations per week, that would run for about 19 years of use, which is pretty long time for a hobbyist project that you use once a week. But consider a super motivated amateur radio contest operator making thousands of contacts over a contest weekend. If you use this as a transmit receive relay, it would exceed the datasheet specs in like maybe one weekend. So You can see why professional transmit receive relays cost like, $100 each because they last forever, almost. Anyway, in summary, relays are mechanical parts and mechanical parts wear out, but sometimes it takes a really long time. You can talk to an old telecommunications engineer about the history and a lot of mythology about sealing current, but in summary, mechanical contacts will eventually oxidize, especially silver, and a small voltage and very modest current will help kind of spark and clean the contacts to receive it so you'll get a low contact resistance. It turns out if you just flip a relay on and off and only send like um, audio signals through or something, it'll eventually corrode. Even the mechanical force of smushing on and smushing off, it'll still corrode. But if you put a little sealing current through it, it'll create just a tiny little bit of spark, and that'll keep the contacts clean for almost ever. The data sheet for the relay specifies if you run about 6 volts across open contacts and push about an amp through closed contacts, then you'll get the optimum 10,000 or so switching operations with a resistance below a tenth of an ohm. But if you don't run enough current through the contacts, eventually the contacts resistance will increase. Finally, the data sheet specifies this is a sealed relay, but not a dust-proof relay. So I'd be careful around woodworking appliances or dusty environments. Something that makes a big pile of sawdust and then mix it with a bunch of sparks. It might be bad. Um, but it is sealed, generally speaking, from the elements. It's just not industrially sealed for, you wouldn't want to use it in like a gas pump or something. Some more free design advice worth every penny. The datasheet claims 100 meg insulation resistance at 500 volts and less than 1 milliamp current flow when applying a kilovolt to the contacts for a minute. So if you're doing something weird like switching Geiger counter tubes, this might not be your best bet. It's probably good enough for pH sensors. On the other hand, its insulation is rated to 10 times better than my multimeter input impedance, so it'd be more than good enough to switch the inputs in my benchtop meter. Note that the datasheet implies it'll hold a kilovolt AC across open contacts, but can only achieve its rated 10,000 switching operations at a mere 250 volts AC. The datasheet doesn't give DC specifications for contacts. The DC ratings of old relays is sometimes very low because the contacts relied on 60 hertz AC voltage and current dropping to zero to extinguish the arc. The physical case of the relay claims up to 30 volts at 10 amps. I wouldn't exceed those specifications, or the relay may not be able to break the arc and turn off after it's been turned on. You might be able to hold off a kilovolt when open, but when closed, it might not be able to open against a kilovolt. It's only guaranteed to 30 volts for opening. Also, the data sheet describes 250 volts AC, but there's no such thing. I assume they mean RMS, like wall outlet voltage. That's 707 volts peak to peak. That's a lot of voltage to switch, so stay safe out there. Please help us fund the development of Node-RED related software by donating on our project's Patreon page. You can find a link on the Spring City Solutions Node-RED project page or scan the QR code below. Here's a review of the topics we covered in this video. We examined the hardware, then we demonstrated several Node-RED application flows that you might use for your own projects. Some free project design advice worth every penny you paid for it. Finally, if you could donate to the project, that would be great. If you need to contact us, this project has a dedicated email address at Spring City Solutions. It's nodered@springcitysolutions.com. Raspberry Pi is a trademark of Raspberry Pi Trade-In. Keyestudio is a registered trademark of Shenzhen Keys DIY Robot Co., Limited. Node-RED is a trademark or registered trademark of the OpenJS Foundation in the United States. This was a Spring City Solutions production, copyright 2021. Thanks for watching.